Welcome everyone. So this is our 116th live stream geometry. We've been doing it over 2 years. So we have me and 6 other people here with us. And today I'm going to do some problems from the China team selection test and others from various contests sent to me by Yusuf, so one of the participants on the channel right now. So if you want to join us in the future, feel free to email me at mgreenv801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. All right, so with that, I am going to share my screen. Just a second. Let's see. Hold on. Give me just a moment. Someone else just sent me a message, so that's why I paused it for a second. Share my screen. So many people are all trying to join. All right. So here is the first problem. Can you all see it? So this is from the China team selection test in 2012, and it looks like a lot of different people are joining today. So we have a triangle and an end circle, which touches it at B, E, and F. So I've created a tool that does that. So it should give us all 3 tangency points, D, E, and F. It's called engineering. Okay. And we reflect D over EF, E over FD, and F over DE. So we use this tool. Reflect D over EF, F over DE, and E over FD. So that'll give us a bunch of kites.
I want to say that I kind of solved this problem.
Oh, really?
Yeah, just because we already did a problem related to this.
Okay.
Basically, you have 3 points and you can work with just one and kind of solve the problem because of that. So if you intersected AL with BC, then that point would lie on line OI. That's the thing of the problem.
So that would lie on OI, where O is the circumcenter of ABC?
Yeah.
Okay.
I'm not exactly sure how you can prove that. I mean, I forgot the proof, but yeah, as you can see, that is enough to show the problem.
Okay, interesting. So let's see if we can remember the proof of that. That's a really interesting fact. Okay, so if we reflect D over EF, and then we intersect it with BC, it lies on line OI. All right. I did not remember that, but yeah, I'm sure we did it before. My memory is just not as good as it used to be. Let's see. So this is obviously a kite. DL is perpendicular to EF. And this point, we know, I think G, what do we know? So this is the Sharky Devil configuration, right? Let's draw the circle. So we know that GI and that point are linear. That's from another video on my channel. Let's see. But yeah, it almost looks like H. I don't want to make it look like H lies on FL. So maybe that looks okay.
Even though that it kind of is related to Shark Devil, I wouldn't say that that collinearity would help us a lot.
OI and P being collinear?
No, I, J, and H.
Oh, I, G, and H. Maybe GEO is parallel to PH. Yeah, it looks like it. Okay, so we can show GEO. Let's think about that. So we want to show IO and P are collinear. If we could maybe show some kind of homotopy, like maybe GI over GO is HI over HP or something like that.
Could you move the diagram
Yeah.
to see if is it actually true?
Oh, you want to see if they're actually parallel? Okay. Oh, they're not. You're right.
Yeah.
Yeah, that's a really interesting observation. That P lies on IO. I guess another way to think about it is we could let IO meet BC at P prime, and then show LA and P prime are collinear.
Could you repeat?
Oh, I was just thinking working backwards. So let IO meet BC at P prime, and then try to show LA and P prime are collinear.
Yeah, I think that is also better, and I have a suggestion of how we would do that.
Okay.
So yeah, define P as intersection of OI and BC,
Okay.
and then we draw the midpoints of arc BC, the small and big one.
Okay.
So now, because O is the center of that segment, the midpoint, then we can project through I, we can project JK O infinity.
JKO infinity.
Yeah, onto BC.
Okay. So let's see.
Well, obviously AI and J are collinear.
Oops, sorry. One more person is joining. Yes. Okay, so we're projecting it onto BC, right?
Yeah.
So this is the foot of the angle bisector. Let me call it R instead. Actually, let me rename both these. Let's call it. Hang on, I'm running out of letters. S and T. All right.
Yeah. Okay.
I guess I could draw. This is the touch point of the mixed linear in circles, so I'll just draw it anyways. Okay.
Okay, and then we could project through A. So by this projection, you have that TS, D, P prime are harmonic.
Mm-hmm.
So you project those four through A onto the line DG. So firstly, D stays the same, S goes to infinity, P prime should go to L. if the problem were true. And that means that T must go to G.
Okay.
So if we knew that A, G, and T are collinear, then the problem would be solved
Interesting.
because of that projection. And
Okay.
I remember that T, G, and A collinearity is kind of well known, but I don't remember how to prove it.
Yeah. It seems like I think it's just a spiral similarity because AFE is similar to KBC, and we want to show like G corresponds to T. And that
Mhm.
probably doesn't seem that hard.
Wait, why would we need G and T to be corresponding?
If G corresponded to T, actually, that's a good question. I just kind of guessed, but maybe,
I mean, it makes sense, but I don't see exactly how that
yeah.
is enough.
Let me check that that's actually true. Um,
I'm pretty sure it is true, but yeah.
no, it's not because if it was, then we'd have ABTK as cyclic.
Oh, yeah. Actually, D and G are corresponding.
D and G are corresponding.
Yeah, that
So
actually is true. That D and G are corresponding.
yeah, so we know that AT and KB meet on the circle, right?
Yeah.
Maybe that helps. So, and we want to show.
Mm.
So I guess one way to do it, we want to show that FAG equals like BAQ, but FAG is BKB. So I guess yeah, we want to show. Just thinking about how to do this.
You know, in the worst case scenario, we can just bash it kind of a bit with a bit of trig. Because
Okay.
we can calculate BT over TC. It is UB over UC. And UB over UC is something normal.
BT over TC is UB over UC.
Yeah.
Yeah, I was single bisector.
Yeah. And maybe you can calculate BT or TC using the angle BAT, actually BAG.
Okay.
But yeah, we don't want to bash.
Yeah, there has to be a synthetic way. So let's think about this. I guess what we could do is we could try to find, if we define T this way, we could try to find the cross ratio BT-BC, and then we could define T prime this way, and we could try to find the cross ratio BT prime DC, and if they're the same, then they have to be the same point, right?
Yeah.
So
we would need the intersection of AD and EF.
AD and EF, yes. Wow, this must be, I don't, so many people are joining. Okay, so let's see. So yeah, AD and EF. I'll draw that. There we go. And let's call it something, let's call it V.
So BTDS is FGVE.
Yes. And is that FGVE? And then we could project those through D onto the circle. I don't know if that helps. So
Maybe onto the line AI.
on the line AI. Okay.
Yeah. Then we get Iran lemma and 1 point in infinity.
Okay. Oh, and so that presents harmonic, or let's see.
Well, it isn't harmonic.
It's not harmonic.
Yeah, we just took some random cross ratio. We want to kind of get it in 2 ways.
So FGV, or we could also project those through I, even onto this circle. So FH, but yeah, okay. So for point V, so you said projected through, projected onto line AI through D, right?
Yeah.
Okay.
Then we will get intersections of DE and DF, which are not too good, but at least we get 1 point in infinity.
Okay.
Also, if this doesn't work, maybe we can project through A to the circle ABC.
Project through A onto ABC.
Yeah, because we want to use that A, G, and Q are collinear.
Yes. So that would be BC, W, and Q, right?
Yeah.
And
So we
now
want
let's
to show that BCQW is BCUQ.
is BCUQ. Yes.
And how do we do that?
Let's see. So W. Yeah, what do we do with W?
You know, there is one maybe useful thing we can use for point W. If you reflect W over the line KJ, then that point would be the touch point of the mixed linear X circle.
Oh, really?
Yeah.
And this is a touch point of the mixed linear N circle, is U.
Yeah. So maybe because of that, we get some correlation.
And also for BCUW, we could project those through D onto the circle. And we get BCA, and it's well known that this point is like the parallel from A to BC, right? So if we take BCUW and we project it through D onto the circle, we would get AZCB, right?
Yeah.
And then if we take this BCWJ and we reflect everything across this, we get BCW prime J. Okay, so you said this is a mixed linear X circle touch point.
Yeah. So because basically everything for the X circle, the mixed linear X circle works the same as in the in circle, then V prime Z would pass through the touch point of the X circle with BC.
But wait, we could also, sorry, so this is my other idea, but we could also project through D. So like BCWQ, if we project through D, that would be BCAK. So we could show that BCAK is BCAZ. Is that right? Or
maybe you just messed up some cross ratios, but yeah, that idea looks great. So we need to show that the BCUQ is BCQW.
Yeah.
So if you project, then we want to show that CBZK is CBKA.
Yeah.
That looks true. Just like we have parallel line, midpoint. That must be obvious.
Yeah.
Okay, so we basically solved the problem.
But wait, how do you, so we still have to figure that out, right? So.
But yeah, but now you can just use the definition of cross ratio, and that's it for sure. You just take the ratios of segments, and that must be it.
Okay. But there must be a way, like, let's see. So BCAK, we can project through J onto BC, and we get BSCA1. Let me call this.
Yeah, but there really isn't any need to complicate.
Okay.
It really is obvious when you have those two cross ratios. So let's say we want to calculate cross ratio CBZK. That is equal to ZC over ZB divided by KC over KB.
Oh, okay.
KC over KB is 1. And in the other one, you would just get KC over KB divided by AC over AB.
Oh.
And that's it.
Well, one of them was BCZA. One of them didn't have a K, right? Or did they both?
No, both got K.
Oh, so then it's just a reflection, right? So, but
you can say that also.
So both of them. So we want to show BCUQ as BCQW, or both of them had Q in it.
Yeah.
Oh, okay. So then it's really obvious, yeah, because you're just reflecting the whole figure across JK. Okay, so that's all.
Yeah.
All right, so I'm gonna write it up. Okay. So let IO meet BC at P prime. Okay, and then what we'll do is we'll project. Okay, so basically we want to let KI meet BC at T prime, and we want to let now I'm confused. So okay, we projected through we projected KOJ through I. So projecting through I onto BC. We have so KOJ infinity is TP prime SD, or KJ that would be TS P prime D. And then we want to project that through A. Okay, so really we work the other way. We want to show, I forget what we did next. So GV
So P prime needs to go to L. That is the problem. And
oh yeah, so we're projecting through A and we need to show it goes to L. Okay.
yeah, so we need to show that AG and T are collinear.
Yes. Okay, so we project those through A onto DG. So we get DG infinity and L. Okay, so we want to show that A, P prime, and L are collinear. And which is the same as saying that AG and T are collinear. Okay, so first, so let KI intersect it at T, and let AG intersect BC at T prime. So first we'll calculate BT DC, and we do that by we first project through K onto the circle, and then we project this. Okay, so BT DC, for I don't know exactly how, but is equal to BUQ and then we project through D, so that's CZKB. Okay. So I'm gonna.
It is BCUQ, not BUQC.
Oh yeah, you're right. BCUQ, and that's CB ZK. I think that's right.
Yeah.
And then let AG meet BC at T prime. Oh, we have a really big group today. So, and then we have BCT prime D. Is equal to FEGV. FE GB. And that then we project through A, so that's BCQW. And then we project through B, so that's CB KA. And then if we reflect over the vertical axis, that should be BC KZ or BC AK. Let's see, CBKA.
It is BCKZ.
It's BCK. So BC, oh, because K is fixed. All right, so that means these two are equal, so that means that T prime equals T. And once we know that, then we can project through A onto DL. And so projecting through A onto DL, it's a lot of projections. Then we have TSDP prime. Let's see, we want to show P prime goes to L. But basically, we know that this cross ratio is -1 up here. So yeah, we could kind of switch the order of how we do things. So I'm gonna just move stuff around. So this would be -1. And then we could project that through A. So this would be equal to G infinity, and then the intersection, and then D. So it would be G, and then G infinity, and then, whoa, what happened there? Oh, I didn't finish it. And then AP prime intersect DG, and then G or D? What did I leave out? So I think it would be like this, but somewhere I messed up here. So let's see, what do I need to change here? Oh,
With the wrong bracket.
Yeah, the wrong bracket. Okay.
Also, it is a DG infinity, not AD infinity.
Oh, you're right. So that implies that this basically implies that AP prime intersects DG at L. Because in order for this to be harmonic, like since this is infinity, G has to be the midpoint of LD, and so let's see, where does this go? There we go. So just do it something like this. Just put both of them. So once we know that, basically we know that P prime equals P, so P lies on OI. And then similarly, Q and R lie on OI. And then that means that P, Q, and R are collinear. P, Q, and R are collinear. So yeah, this is a fun one. Yeah, I think I do remember us doing something like this before. There's a lot of points I didn't write exactly what their definition is, so I'll just say label the points as shown. All right, so let's move on to the next problem, unless anyone has questions.
There is another way to show that AGT are collinear.
Oh, what?
Can you hear me? Can you hear me?
Yeah, I can hear you.
Okay, so introducing the point BC and the intersection line tangent at I2, like AH and BC intersection.
Okay, AH and BC. Okay, so
yeah,
so this intersection point.
Okay, and level the intersection points.
Okay, so it's A1.
Okay, yeah, A1I is tangent to the circle.
Okay, and yeah, that's not hard to prove.
This is by radical axis theorem.
Oh yeah, because the circumcircle BIC. Yeah, you can use radical axis theorem. Okay.
And now introduce the intersection of EF and AH.
Okay.
Okay. We will basically show that the cross ratio of A on TBC equals 1.
A1 TBC.
Like we will take the, like if T on be the intersection of AG and BC and T2 be the intersection of KI and BC. Then we'll
Oh,
prove
you're showing it's the same point. Okay.
Yes. So now my claim is B1 GEF equals -1.
B1 GEF. Okay.
Yeah, this is true by what? A radical, like taking power of 1.
Okay.
Okay, then project everything through A.
So you get BC, T, and A1 would be harmonic.
Yes.
Okay.
And now forget the point G, and now let T2 be the intersection of KI and BC.
Okay.
Then we'll show that is in harmonic conjugate. Okay, so another claim is like A1, U, and J would be collinear. And that's all.
A1,
A1, U, J.
A1, U, and J. Okay. Okay, so if we define it that way, the idea is, so once we knew that, we could project through U.
Okay, if we know the collinearity, then we are done because we have a right angle and angle bisector.
Okay.
So we have to prove the collinearity. And it should be done by some ratio chasing using Menelaus on like we can take the intersection of the wait. Can you mark the touch point of the intersection circle on AB and AC?
So like this is the touch point of the mixed linear in circle, right? U.
Yeah, and mark the other two touch points on AB and AC.
Okay. I think I have a tool for this. So let's see how this works. Okay, E1 and F1.
Yes. So we know A1, E1, F1 are collinear.
Mm-hmm.
Yeah. Then it seems like Menelaus can help because AE1 equal AF1 and
Interesting. I believe you that it works. So, okay. Interesting. All right. So yeah, thanks for sharing the other way to do it.
yeah.
I'm not going to type up the whole thing, but I always like having more than one way to do it. I like this idea because I've seen this kind of point show up in a lot of problems before, like B1.
Yeah, it is the Q point of the triangle GEF, XQ point.
Interesting. Very cool. All right, so I'm going to move on to the next problem. Lenardi, I think he just showed me in the chat, or I think he just put in the chat a problem. I'm going to first do one other problem, but then I might get to that later. So this one was from the team selection test. So we draw the 9-point circle. I think I have a tool for this. So it has an interesting notation. Oh, I guess I didn't label all the points, but I guess it's kind of okay because I'm going to need to rename them anyway. So we have MA, MB, and MC. This should be MC. And I'll call the center of it N. And then let's draw circumcircle of ABC, and O is the center. This is O, and let's draw the orthocenter. Which is H, and N is going to be the midpoint of OH. So then we intersect. So S is just any point lying on this line. It doesn't have to be on the segment OH. And we let MAS, MBS, and MCS intersect the 9-point circle at X, Y, and Z. And so this will be phi. By the way, does this kind of reminds me of something we did with Steinbart's theorem? I don't know if do any of you remember that video on Steinbart's theorem? I don't know if this is the same concept.
Steinbart
Sure we
for
did
in
this.
circle.
Sorry, hold on one sec. Sorry, what were you saying?
Okay, first then I just want to say that I'm pretty sure we already did this before.
Oh, really?
And yeah, it looks like Steinbart's theorem.
Okay. All right. So if we already did it before, I'll move on to another problem. This one I don't think we have. So let's use the orthocenter tool.
This is IMO 2000 P3, I guess.
2000 P3.
Yeah, this was in the contest.
Okay. Did we do this on my channel before?
No, I guess.
Okay. This is the one you sent. Is this the one you sent me? Sorry, I'm not sure. Oh, Hatem, are you sorry, I'm a little confused who's on. But is Yusuf still on? I guess not. Sorry, Hatem, where are you from? Okay, I'll just continue. So let's see. So yeah, this is from the IMO shortlist in 2000. So that's H1, H2.
Sorry, I disconnected.
Oh,
I heard you. Yeah, this one is problem 6 of 2000.
okay. So it's not just on the shortlist; it's actually on the IMO.
I think also G7. I think.
Okay. So it was G7. So this will be T1, T2, and T3. So I think basically we could just show it for like one side. I think this is one of the problems where we just show it for like one side, and then by the same argument, it's true for the others. So basically, we want to take, we could start with H2H3, and we want to reflect it with respect to these two. And we want to show, let's see. So, well, okay, we'd actually want to take the other two. So H1H3 and H1H2 and reflect it. So let me draw the entire lines. And I want to reflect this line about that. And I want to reflect this line about that. And I want to show that these two intersect on the end circle. Okay. So yeah, I just want to make it clear that this line is a reflection of this over this. So maybe I can draw the diagram in some better way to show that. So maybe like this. That way, yeah, we can see it's the reflection. And now I'll make it a little clearer. So I'll just draw this point just to make things look easier. And why not this point and this point? So we have this, and wait, now I'm just confused. So I don't think that's right. So I have H3, H1, and I reflected it. Okay. So yeah, we want to show that this T3E and JD like meet at point F on the end circle. Okay, so actually now I'm confused. I don't even know which is I and which is T. Okay, so I switched the labels for T3 and I, so it should really be like that. I guess point I is not really part of the problem. Like you just take this line and reflect it, but I just wanted to make it look nicer. So yeah, this is like this line bisects this angle, and this line bisects that angle. It's kind of interesting. So yeah, H1, H3 intersects T1, T3E, and H1, H2 intersects T1, T2 at D. And then you like reflect those two lines and you want to show it meets on the end circle. Yeah, it's a very, very odd problem. I wonder. Yeah, we want to show the reflection of two lines meet on an end circle. Still on. Yeah, so can we say anything special about F? Maybe if we take the anti-Steiner point of F, it's something special. That's just a guess. So let's see. I'm just completely guessing here, but what if I took the anti-Steiner point of that line? Because with all these reflections, that just makes me think of the anti-Steiner point. So if I reflect so those are the three reflections. Is there anything special about this point right here? And maybe there isn't, but I was just curious. I don't think so. But yeah, maybe, yeah, we have two different reflections. So maybe it's an anti-Steiner point of some other triangle. Because it looks, doesn't it look a lot like an anti-Steiner point problem? So we have this triangle, H1, H2, H3, and we're reflecting. Or we could look at T1, T2, T3. So I wonder if we take T1, T2, T3, is F the anti-Steiner point of some other line through the orthocenter of T1, T2, T3? I'm not sure.
So
Let's see. So Mai just asked the question. He said, if we reflect F over this line, is it T1? And I think it is. Yes. So, oh, Coffee, your screen is, you're sharing your video, just letting you know. But I could turn it off if you want. Yeah, so it looks like T1 and F are reflections across AG. I don't know why that's true, but it looks like it's true. So maybe it's better to define F that way, reflect T1 over AG, and then we want to show that I, E, and that point are collinear. That's probably an easier way to do it, right? Yeah. Okay. So yeah, you reflect it, and then we could get rid of a lot of the figure, if that were the case. So we could get rid of all this. And we just want to show I, E, and F are collinear, which seems a lot easier. Let me try to make T and F farther away. It's not that easy to do that, but okay. All right, so just so I don't have to look at this whole line, I'm going to label this, whoops. So let me label the foot of the angle bisector, K. And I'm just going to draw the segment AK, so we don't have to keep looking at the whole line. Okay. So KF is going to be tangent to the incircle by symmetry. And if we reflect T1, T2, T3 with respect to AG, BG, CG. Okay, so you're saying put all of the reflection points. And then we should get a triangle. So if we're reflecting all three, let's see. I mean, really, if we just have point F and we show IE and F are collinear, that would be enough to solve the problem, right? So is it worth drawing all three of them? I could do it just to see, but I don't know if there's anything special about triangle KLM. Is LM parallel to BC? Let's see. Oh, it looks like it. So maybe that was kind of your hint. Is LM is it looks like it's parallel to BC. And then if that's true, then KLM is parallel, is similar to ABC. Okay, so I'm going to keep L and M. Let me draw these points. So what were we saying? We were saying, sorry, FLM is what would be similar to ABC. So yeah, I don't know if that's obvious. You know that KF is tangent to the circle, and so is NL, and so is OM. So we'd have a bunch of harmonic quadrilaterals then, right? If we drew like this point and this point and this point. But yeah, first let's see if we could show, let's go back to what we were trying to show originally. We want to show M, E, and F are collinear, right? Or was it, I forget, if it was, oh, it's I, E, and F. Or, sorry, I'm losing track here. How did we define I? Oh, this is just, we want to show this line passes through F. So another way to say it is we want to show that ET1 bisects H1EF. So I wonder if there's something, sorry, go ahead. We want to show this as an angle bisector.
Isn't the reflection of H1 through T1, T3 through lies on
Oh yeah.
yeah.
Is that a well-known fact? Let's see.
No, I actually guessed it.
Interesting. Okay, so reflecting H over T1, T3, and we're saying it lies on the angle bisector. Yeah, that feels like it shouldn't be hard to prove, right?
Yeah.
We could show that, we're done. So we could hide like a lot of the diagram That's all we have to show.
So yeah, if we show that they are collinear, then I think we're done.
Yeah.
Or like, no.
I wonder, is H1EP similar to like K T2 T3? It's just a guess. I don't know if that's true. So H1P would be like perpendicular to T1, T3 in that case. So it would be like parallel to BN. So there's a couple different ways to think about this. So yeah, we would draw a parallel through H1 to BN, and we let it intersect the bisector at P. That's one way to think about it. I think we're really close. Let's see. So yeah, should I just hide a whole bunch of stuff in this diagram? Like there's actually very little that we need. I'm just gonna go hide a whole bunch of stuff because all we really need is a couple points. Might make it easier. Yeah, we don't even.
I think we need H3.
We need H3
Yeah, I think so.
because aren't we just reflecting H over T1, T3, and then we want to show it lies on the angle bisector?
Yeah.
So I think we we want to keep that one, but we're just saying you take H and you reflect it over T1, T3, and then you want to show it lies on the angle bisector.
Can you draw the intersection of T3 and T1, line T3, T1 with AG?
Yeah.
With the angle bisector?
Yes.
let's say it's G prime. Okay, Q. Mm.
Just gonna make these segments. Okay, so So yeah, we want to show QP equals QH1. That's one way to say it. We can take F reflecting T1 through AG. So T2F passes through Q. Okay. So if I reflect T1 over AG and I call it F, so then you're saying T2F passes through Q. Oh, so that's true by symmetry. Okay. And then Q, H1, H2, AC belong to the circle. So is that like the Iran lemma? Because it's where the angle bisector meets this. Yeah, that's the Iran lemma. So Q, A, and C is a right angle. Q, yeah. So those all lie on a circle. And then we want to show R is the midpoint of H1P. So that's the same as saying that we want to show this is like an angle bisector, right? Then we could take S reflecting F through T1, T2. Hold on a sec. Okay, so reflect F. Okay. All right. Call that S. S lies on H1, H2. Okay. Wait, or H1, H3. Does it have to be like I wonder if it has to be this hard. So okay, but anyways, okay. So like yeah. So we want to show S lies on H1, H2.
QC, T1, QC.
So reflect F through T1, T3. Okay, so I'm going to delete this. So we reflect F through T1, T3. Okay, and then
We have T1, G, Q, and C. T1.
are cyclic. And
cyclic.
T2.
That's because T1 Q G is equal to half of C.
Yeah, they're all right angles. So so it has to be. Okay. Oh, and then it's clear that this is an angle bisector. But does that solve the problem? Because GT1 equals GT2. Yeah. I wonder if that just solves the problem. I think it does.
So
Oh, what?
so if P lies on AQ, then we're done.
Yeah.
So
And
we have A, Q, and C is equal to 90, as we, since that's the center. I mean the diameter. We have A and C,
yeah.
which is, and also we have A and H1 and C is equal to 90. So we have a cyclic quadrilateral, A, H1, Q, and C, cyclic quadrilateral,
Yes.
which and also we have H1, Q, and G is equal to it's equal to angle C, and
Yes.
it's equal to it's equal to 2 2 T1. Where's the T1? No. Yes, we said that T1 Q G is equal to half of C, which implies so we have
That solves it.
H1 is H1 Q G H1 Q G is equal to 2 T1 Q G, which implies
Yeah, so we could show T1QG is half of H1QA, and then that would show that this is like an angle bisector.
yeah, so we have Q1 bisected.
Yeah, okay, so
Which one?
What do you want to show actually? I am confused.
okay, I think we have two different solutions going on. So I think my Nguyen is giving one solution. Let's see, QH1 is the bisector of P1QS.
Yeah, so we have yes, sorry.
Maybe I'll type up both solutions. Okay, but
We have Q and QT1 bisects angle H1, Q and
P. Yeah.
P or G, same thing. So doesn't that, which implies that P lies on the angle bisector?
Yes. So that solves it. So okay. So first I'm going to type up Yusuf's solution. So Yusuf's solution. I don't think we need this circle right here, and I don't think we need point S for his solution. So for his, we show that this is cyclic. That's a well-known lemma. and this is cyclic, which follows because these are all right angles. And we know that this is a right angle because of this one being cyclic. And then once we know that these are both cyclic, it's easy to show that QT3 bisects this angle because we can calculate angle H1QA using this circle. We can calculate angle T1QG using this circle, and we could show it's half of it. And so this is an angle bisector. And so basically that solves the problem, because then we show the reflection of H over T1.
Okay.
Yeah.
I have easier solution. Like we don't need even the other points. Like if we take the intersection CG and the circle with diameter SG.
The intersection of what?
CG and T1, T2. Sorry, T1, T3.
Okay.
It lies on the circle of diameter SG. This is just Iron lemma.
Okay.
And then done, because AQT equal half of C and H1QT equal HCT equals half of C.
Okay. So that makes it really fast. Okay. So
Yes.
then we only need one of the circles. We don't need,
We don't need any other.
well, we want this circle. We want this circle, right?
We need this circle, this big circle. But
Okay. So let me call this X. So basically, both of these points lie on that circle, and then from there, it's easy to show that this is an angle bisector, and or it's easy to show that this bisects this angle. So that means if you reflect H over T1, T2, it lies on the angle bisector, and I forget. Okay, so let me first write that up. So draw the circle with diameter AC as shown. Okay, so I'll say by a well-known lemma, CG and T, three and AG intersect T1, T3. Okay, so sorry, this is that would be AG intersect T1, T3. So AG intersect T1, T3, and CG intersect T1, T3. Lie on the circle with diameter AC. Okay. So from there, angle H1QA is equal to angle H1CA, and angle H1QX is equal to angle H1CX. H1QA is equal to angle H1CA is equal to 2 H1CX let's see, G. I don't know why I called the in-center G, but oh well, it's too late. Which is equal to 2 angle H1CX. I'll just make this an X, which is equal to 2 angle H1QX. Okay, so that means that QX bisects angle H1QA. And then basically we had that, I think we had that Q, okay, so what did we do after we had that? Then we knew this was an angle bisector, so we know that if you take H1, so if you reflect H1 over this, you get P, which would lie in one bisector. I forget how we solved it from here. So, oh, because T2 is the other reflection? Is that the idea? So, sorry. Oh, because so we wanted to show that this is actually the reflection of T1 over the angle bisector. We wanted to show that's what F is. And that's true by symmetry. So by symmetry then, since this is an angle bisector, okay, so this proves that the reflection of H1 over this lies on angle bisector. And if that's true, then that means that F is the reflection of T1 over the angle bisector. So that means that...
Yeah. F is a reflection of T1 by the angle bisector, and it's the same for the other points.
Okay, so...
which implied the reflection of T3 and T2 over the angle bisector also lies on circle, the in circle.
Yeah. So how did we define F originally though? Because it's obvious that if you reflect T1 over the angle bisector, it lies on the in circle. That's trivially true. Because this line just passed through the center of the circle. So how, I feel like we defined F a different way. Oh, if you let it be Q T2 intersect the circle. Okay, so yeah, now I'm just confused. Okay, so if we reflect H1 over this, it lies on this angle bisector. If we reflect H, so let me draw H3 again. If we reflect H3 over this, then it would lie on this angle bisector, right? And so we've shown that both those lie on those angle bisectors. Then we want to show that I'm just confused. I know we had it. I just forgot how we got here.
No, so we proved that P lies on the angle bisector, and what we forgot to prove is we want P also to lie on F and reflect on the other one. You labeled it as M before, but how you deleted it?
Okay.
No.
So, sorry.
I think April.
So yeah, I'm gonna unhide the other. It all disappeared. I don't know. Okay. Oh, we have H1, H2, and H3. But so we wanted to show PF lies on something else.
We need no, we want to prove that P lies on F and there. Just a second.
Okay. Let's see. It was like. Okay, let me draw an H1, H3 again. I think it was maybe like that. So we took H1, H3. We reflected about that. Okay, so
can you draw the reflection of T3 with respect to CG?
okay.
Yeah, so we need to prove that P lies on S prime and V.
I don't even. So I think I've solved this. So basically, we've shown if we let S prime be the reflection of T1 over the angle bisector, then we've shown that Q, S prime, and T2 are collinear. And then I think by the same argument, we could show that U, S prime, wait. So okay, so okay, so if you reflect T1 and T2 over the angle over now I'm just getting confused.
I think like after we prove that P lies on the angle angle bisector, we just need to prove that P lies on V S prime to finish that.
ES prime. Yeah, so okay, so I think here's what we did. So step one is to show that basically we've shown that QX bisects H1QA. So therefore HR equals HP. And therefore, we want to show that this is an angle bisector. So H1UP. So we know that this one is an angle bisector, and we want to show that this one is an angle bisector.
You mean UQ?
Yeah, we want to show UQ bisects H1U S prime. Well, or is that obvious? Well,
Yeah. We
my brain hurts.
no, I think we did that, but we forgot how to.
Yeah.
So we have H1 and Q and H1 Q G is equal to. We said that it's equal to C.
Yes.
Yeah, it's equal to C. And also we have T1 QG. T1 QG. Yes, T1 QG. It's equal to T1 QG is equal to half of angle C,
Yes.
which is also equal to T1 T1C and G, T1CG, and we said that T1Q, C, and G are cyclic.
Yeah.
Yeah, and we said, and we also said that H1, H1Q, and C cyclic because we have 290 degrees,
Yes.
which implies that H1, Q, and G is equal to C, which is equal to T1 T1 QG, which implies that it's a bisector.
So you mean that QX is a bisector?
Yes.
Yeah, so that I know. That one I proved right here. And we don't even need those two circles. Like this proves it without even using this circle, that this is a bisector. So that I understand. Let's see what time it is. 10:40. All right, let's spend another couple minutes. So we know this is an angle bisector. We also know that this, if we define it this way, that would be an angle bisector. This problem drives me crazy. I don't like it. I don't like how confusing this is. But yeah, I know we had it earlier. I just don't remember what we said earlier.
Of course, we won't remember what we said. This problem is all about intersections, and I mean, like reflections.
Yeah.
This one's reflected in this one, so it's kind of messed up.
Let me think. So somehow, like, if we can show that, so we take H1, H3, we wanted to show if we reflect it over T1, T3, it passes through S prime. And then we could use the same argument for H1, H2, and then that would solve the problem. So then we just took the reflection of H1 and we said, we just want to show that U, P, and S prime are collinear. And we know that this is an angle bisector. And okay, so since this is an angle bisector, this was also an angle bisector. So all right, you want to just move on to the next problem? I feel like we've spent a while on this one.
Yes.
Okay. This one I think might be a little easier. So